Their footprints display well-developed arches, with heel and toe prints that could only have been made by someone walking on 2 feet, very different from those of upright chimpanzees. The Laetoli footprints provide a glimpse of early hominins, and their discovery in the 1970s led to the bombshell realization that bipedalism, walking on 2 feet, preceded growth in brain size and not the other way around. Researchers realized that upright walking meant our hands were now free. This meant we could make things, and creativity is a key attribute of our human family.
Hominidae and Homininae.
First, some genealogy. We humans are members of the order Primates, which includes 2 suborders, one of which includes the anthropoids, which incorporates apes, people, and monkeys. Further up the genealogical pyramid, we belong to the superfamily Hominoidea, which also includes gibbons, gorillas, chimpanzees, and the bonobo.
Within the hominoid superfamily, there's a division between Hominidae, which includes African and Asian apes, as well as us. We belong to the Homininae, or hominin tribe,
which includes modern humans, earlier human subspecies, and their direct ancestors. To date, researchers have identified over 20 hominin species, but only some of them are our ancestors, many becoming extinct without giving rise to new species. At any given time over much of the past 6 million years, several hominin species coexisted. A species is typically defined as a group of organisms that can provide fertile offspring. It was only after around 30,000 years ago that the other human species became extinct and only we, Homo sapiens, remained. But, given the scanty archaeological record for the early period, how do we know when hominins separated from non-human primates? In the beginning. By 14 MA, Africa's climate was much drier than in earlier times. Hard fruit and grass-eating hominoids flourished throughout East Africa between 8 and 5 MA. They spent much time on the ground but walked on 4 feet. Unfortunately, we know almost nothing about these hominoids. They lived at a time of major environmental changes, including cooler temperatures and more open, as opposed to wooded, terrain. Today's humans are the descendants of these generalized common hominoid ancestors. As forests retreated and tropical Africa's climate became drier, they adapted to much more open savanna environments. This was when early hominins became bipedal, perhaps because they spent more time feeding off foods on the ground. Bipedalism meant that walking assumed great importance for foraging over wider areas. In adapting to drier environments, early hominin populations with their bipedalism could cover longer distances and had improved endurance. Apes, which were adapted to forested environments, stayed in the trees. In contrast, bipedal hominins, who potentially evolved around 6 MA, expanded the range of territory where they obtained food. They broadened their diets, now including more meat. The long-term solutions to living in the savanna meant exploiting patchy and widely distributed foods, while depending on reliable, and often hard to find, water supplies. The hominins were constantly on the move, with meat now playing a more important role during seasons when plant foods were scarce. Most experts believe that East Africa was the main center of early human evolution. It is here that the greatest number of early hominins have come to light. But future fossil discoveries may complicate this scenario. The now desert environments of Ethiopia and northern Kenya were open savanna grassland and woodland that teemed with herds of antelope and other mammals. These were prey for lions, leopards, and other predators, and also for our early hominin ancestors. We know almost nothing of these hominins except the little-known, probably bipedal, Aronin tugenensis, who lived about 6.5 to 5.6 MA. There is also Sahelanthropus chadensis, of Central African origin. The latter may date to 7 to 6 MA, which would place it at around the time of the likely divergence of the hominin lineage with that of the chimpanzee. The date of this split depends less on the Spartan fossil evidence and more on genetic analysis of modern humans and modern chimps. By recording the amount by which the genes of the two species have diverged, geneticists theorize the time of our split. This method of timing, known as the molecular